Hi, I'm Seth Chandler, Professor of Law at the University of Houston Law Center. This is another in a series of videos for the course Analytic Methods for Lawyers, and it deals with valuation of lawsuits. It's going to build on our understanding of statistics and statistical distributions that we've developed during some of the previous material. Okay, so let's start out. We have a lawsuit, and we're going to assume that the damages are distributed uniformly from $0 to $1 million. That is, it's equally likely that the damages will be $397,423 as it is that they'll be $823,906, but there's no chance of them being $1,100,000. So this may be highly unrealistic, but it'll give us off to a start. And in the Wolfram language, we can model this as a uniform distribution on the interval 0 to 1 million. We'll call that script J. All right, so now our kernel knows about that. And you know what? Let's do good hygiene. Let's quit our kernel, make sure I don't have any lingering stuff from some previous work today. All right, everything's sort of turned back navy, meaning that there's nothing there. And we'll reevaluate and get the kernel fired up again. Okay, so one thing we could do is we could value the judgment by computing its mean, okay? And if we do that, you probably don't need me to do this for you, but if you do that, it's $500,000. That's the arithmetic average of all of the possible judgments. Now, if everybody was risk neutral and people were perfectly rational, a case might settle for $500,000, but oftentimes people will settle for less because they're risk averse. Now, what exactly I mean by that is a little bit tricky, but one thing it might mean is that they have a utility of wealth function that exhibits diminishing marginal utility. That is, the increase in happiness they feel in moving from $10,000 to $20,000 is more than the increase they feel in moving from $90,000 to $100,000, and is in turn more than they feel in moving from $970,000 to $980,000. It's not their utility, their happiness isn't a straight line. It sort of curves, bends downwards as we move to higher levels of wealth. So how do we value a lawsuit in the face of diminishing marginal utility of wealth? Okay? So I'm going to teach you a couple of methods in this session. One is the method of certainty equivalent wealth. And the method of certainty equivalent wealth asks what amount of money, if given to the party in question with certainty, would provide the same utility as the party receives from a distribution of possible amounts of money to be received. So one way we might model diminishing marginal utility of wealth is to say that one's utility was proportional to the square root of one's wealth. So let's actually look at what that square root function looks like. And you can see it has this feature that although it keeps going up and up and up, the slope, the rate at which it goes up, seems to diminish the higher and higher we get. We can also verify that the function is monotonic, meaning it's non-decreasing over a certain domain. And there's a Wolfram language function. We haven't seen it before, but it's called function monotonicity. You put in the nature of the thing you're seeking to test, whether it's monotonic, any constraints that might exist here. We're going to constrain x to be greater than 0. I do not want to get into square roots of negative numbers. And what's the variable in this expression? It's x. So if we do this, it's going to tell us 1, and 1 means, yep, it's monotonic, going up. All right. So we could write a function that computes the square root. We'll just call it u. This is not very hard. And now what we might want to do is we might want to compute the expected utility of our judgment function. So what we're going to say, and you need to hearken back to our discussion of expectations, maybe we'll review those materials if this is unfamiliar to you, is we're going to say, what is the expectation u of x, square root of x, where x is distributed according to script J, that's that uniform distribution. And here I'm just going to have it print out the numeric value, and then I'm going to have it return an exact value. So if we do that, it's 2,000 divided by 3, which is 666. That's the expected utility that we're going to get from this judgment. I wonder if there are any other distributions which, when we take the expectation of the same utility function, we end up with this same number of 2,000 over 3. So I'm going to try kind of just a crazy one. I'm going to say that we have a new distribution. We start off with a chi-square distribution with 4 degrees of freedom, and we multiply that by 32 million divided by 81 pi. Don't ask me why, just accept there it is. And we're going to call that script J1, and we're going to then compute the expectation of our same utility function with respect to J1, this wacko transform distribution, instead of our boring uniform distribution that we did before. So let's do that. And lo and behold, looky there. It's 2,000 divided by 3. So what I'm trying to show you is that there's nothing unique about the uniform distribution on 0 to 1 million. There are other distributions which provide the same expected utility to the individual. Let's do another one, okay? Let's take one, it's an empirical distribution. At 2/5 of the time you get nothing, and 3/5 of the time you get 100 million divided by 81. So there it is, and let's compute, we'll call it J2, let's compute our expected utility where we're subject to this empirical distribution. And we get 2,000 divided by 3. And so what we see is that a plaintiff with a square root utility function would in theory be indifferent between a lawsuit, and that should be among for the grammar police, among lawsuits in which the distribution of judgments is script J, the distribution of judgments is script J1, and the distribution of judgments is J2. They all have the same expected utility. But all of these are lotteries. They're all probabilistic. Now, I suppose we could settle a case on this basis. We could say that if the outcome of the case was less than $400,000, the judgment would be 0. And if the outcome was bigger than $400,000, it would be this 100 million divided by 81, which I believe is $1,234,568. And a plaintiff with a square root utility function would be indifferent to that transformation. That would be one way to, quote, settle a lawsuit. But the problem with settling the lawsuit that way is you still have to have a trial in order to figure out what the judgment is. I wonder if there's a way, though, that we could avoid having a trial altogether. Is there a single number such that the plaintiff would be indifferent between receiving that amount and going to trial under the assumption that the judgment distribution would be either J, J1, or little j2? And it turns out there is, and it's easy to figure out what it is. So we're just going to do a little algebra here. We're going to say, find the x such that the utility of having x is equal to the expected utility from each of those lotteries that we saw before. This just says print something out, and this says print out your answer. So if we run this, it turns out that the answer is 4 million divided by 9. We can compute the numeric value, and that's $444,444. And so what we would say is that the certainty equivalent wealth of the distribution J, or actually J1 or J2, under U is $444,444. That's the lowest amount of money that the plaintiff would accept with certainty and be as well off as they would be if they were going to trial. Now, I am fully aware that this is really overly simplistic. There are lots of other issues involved, attorney's fees, bluffing, uncertainty as to various other parameters, but what we've done conceptually is to try to explain how you value a case that is where the outcomes are uncertain. So far, I've had kind of a plaintiff's focus. Let's think about the defendant, and maybe the defendant is also risk averse, so that as the judgment against them doubles, their sense of loss quadruples. And so their sense of loss goes up with the square of the loss. So we'll write a function w that represents that. And now what we're going to do is to say, here's our function w. We're going to say, find the value SU such that the disutility of SU is equal to the expectation of their loss, where their loss is distributed according to that original judgment distribution we had. And just to make the algebraic solver happy, we're going to tell it, hey, that SU better be greater than 0. And we're going to postfix this with a / n so that it gives us a number rather than some elaborate fraction. So when we run this, it turns out that the defendant is willing to pay up to $577,350 to get rid of this lawsuit if it's subject to a sense of loss that goes up as the square of the loss. And so what this suggests is that there's some zone between $444,444 on the plaintiff's side and $577,350 on the defendant's side, in which settlement of the case is advantageous to both of them. Let's ratchet up the complexity a little bit. Instead of using that square of loss idea that I showed you before, let's now assume that the defendant has the same utility of wealth function as the plaintiff. It's just that the defendant has some money. And so their utility is equal to $1,500,000, their initial wealth, less the judgment that they're going to have to pay out. And what we want to compute is that level of wealth which, if held with certainty, would be their expected utility given that X was distributed according to that judgment distribution, that uniform distribution that I showed you earlier. So if we compute that, we get it's $521,795. So that's another way of going about it. Let's look at another scenario. Supposing the defendant has that utility function, that square root utility function, but they only have $700,000, so that a loss of $701,000 is really no different to them than a loss of $700,000. You can't be more than bankrupt is the idea. So in these circumstances, the poorer defendant, let's see how they feel about it. Okay, so what we're going to have is write as a new utility function W3, such that their utility is equal to their square root utility of the greater of 0 or $700,000 minus the judgment amount. And really, I'm not sure why I didn't use script J here. We'll fix that. Okay. And so now we're going to do this same algebra where we're going to say what amount of wealth, if held with certainty, would produce the same expected utility as we see here. And if we run that, we get $547,556. That's the amount of money that our defendant would be willing to pay out in order to settle this lawsuit. They really want to cling to those last dollars, and so they're actually willing to pay a little more in order to avoid going bankrupt. Okay, so far I used a pretty simple utility function, a square root utility function, and I used a really simple judgment distribution, a uniform distribution. So let's see if we can again make things a little more complicated. Supposing we have utility that it goes along with a power law. So u2 of x is equal to 1 plus 2 to the x to the 3/5 power. Probably would be worth plotting that just so we have a sense what that looks like. Let's take this from 0 to 2 million. That's 20 million. And it died. That's because I forgot to evaluate it. Okay, let's evaluate it. And there we go. So that's what it looks like. It has some of these properties I kind of like, which is that it's monotonically increasing. And it looks like the slope kind of declines the farther up you go. So it's exhibiting diminishing marginal utility of income. Okay, let's look at our judgment function, and we're going to have the judgment function be a log normal distribution with a mean of $500,000, a median of $300,000, but it's going to be censored. Okay, you can't get more than $2 million. Maybe that's because there's some law that says you can't collect more than $2 million. Maybe it's because the defendant doesn't have more than $2 million. But there you go. This is our new judgment function, and I'm going to call it J2, script J2. I'm going to actually, I guess, reuse that. Oh, no, I didn't use script J before. I used little j. All right, and so it's doing a little bit of thinking here because it's got to go out to the Wolfram server to get the mean, median, log normal distribution, figure out what that is, and we now have a censored distribution. If you don't remember what a censored distribution is, go back to some of the earlier materials. I believe it is in the basic statistics video and associated notebook. All right, let's now do it's the same calculation. We're going to find out for what level of wealth would the utility under U2 be equal to the expected utility, same utility function, with the judgment distributed according to this censored distribution. And I'm going to ask it to do some algebra here. This is one of the reasons we use things like Wolfram language to do algebra, because no one in their right mind would do this by hand. And it chunks along, chunka, 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 and it gives you a formula that's so big that it doesn't fit on the page. But I did ask for a numeric value, and it's $391,850. And so that is basically what our plaintiff, that's the lowest amount of money our plaintiff should accept under these circumstances. Okay, so that's the method of certainty equivalent wealth, and it's a very time-tested method. If you can come up with some way of figuring out a utility function, and you can come out with some way of approximating a judgment distribution, maybe through an empirical distribution, or a smooth kernel distribution, or something else, you can get a flavor for how much the plaintiff, should accept, and reciprocally, you can get a flavor for how much the defendant should be willing to pay. Another way to model lawsuits is, instead of using certainty equivalent wealth, to use order distributions. Suppose you are very gloomy, and if there are two possible outcomes, you always believe the worst of the two will befall you. Well, that actually lets us use order distributions to model your behavior and your evaluation of lawsuits. For example, supposing the perceived consequence of a lawsuit, or anything else actually for that matter, is the lower of two draws from J. Remember our friend J, that uniform distribution? And so we can write that as order distribution on J, two events, first worst. So let's write that. And we can compute the mean of it. Remember, the mean of J was $500,000, but the mean of the order distribution is $333,333. And so this is a way of modeling some risk aversion. You think about the worst thing. It can be more complicated. Supposing you want to model something as 7 draws and you think it's going to be the second worst. What's the mean of that? $250,000. Let's use Wolfram Language's intelligence and ask it, okay, D draws the ith worst. And we get a nice formula for that. We can now say not just the J distribution, but we can look at any uniform distribution on the interval AB. And we get a formula for that. Now, in many instances, there is no closed form solution for the mean of an order distribution. So, for example, here I'm going to run this, and unless Wolfram language has gotten a lot smarter since I wrote this notebook. It's going to not work. Struggling. All right, and it gave up. But we can also work backwards. Like supposing I think the case is worth $142,000, and I do still believe that it's subject to the distribution J. Are there certain numbers of draws and certain numbers of worstedness that would let this be true? And so I can ask Wolfram Language to find me 10 examples, and it turns out that if I think it's worth $142,000, that is consistent with, for example, me thinking that of the 331,999 draws, I am going to get the 47,144th worst. And that does seem rather silly. And so I don't know if order distributions are the very best way of thinking about risk, but they are an additional way of thinking about risk aversion. And you'll see they provide some intuition for what we're going to talk about next, which is spectral measures. Let's talk spectral measures. It's a little more complicated, perhaps, than certainty equivalent wealth, but it has some major advantages. One of those is, remember our utility function, our square root utility function? Well, what happens if someone's wealth goes below 0 on some calibration scale? You can't really use it because we can't really deal with complex utilities. Second, supposing you have potential outcomes and we say, you know what, we're going to add $100 to every outcome. You might expect that the certainty equivalent wealth would go up by $100 because everything's being shifted to the right by $100. But that's not necessarily the case. With spectral measures, that is the case. And so there are many properties of spectral measures that are desirable. So what is it? Well, instead of writing a potential outcome X from the lawsuit directly and calculating its utility and then calculating its probability and taking an expectation and then reversing out that expectation using the inverse of the utility function, we do something that doesn't require any sort of inversion of functions. Instead of adding a utility function to the mix, we add a weighting distribution. And I'm going to call that distribution capital omega. Omega can be anything, but its domain has to be from 0 to 1, and its PDF, if you're going to simulate risk aversion, has to be non-increasing over that domain. That is, the PDF is higher at lower numbers than it is at higher numbers. And with that, instead of computing the expected value of the lawsuit, you compute the expectation of the quantile function of the original distribution subject to the weighting distribution capital omega. And the notebook sets forth sort of a mathematical or quasi-mathematical formula for the spectral measure. So that's a little abstract and perhaps difficult to understand. So let's look at a simple case. Supposing our weighting distribution is just a triangular distribution and its PDF looks like this, and we can see, hey, that looks pretty good. It's a domain is 0 to 1. It's non-increasing. If we had any doubts as to whether it was non-increasing, we could run function monotonicity over it, a function I think I've shown you before. The fact that it gets -1 means that it's going down all the time. And now we can just, and I guess I have spoiled it for you, and now we can just calculate the expected value of our judgment function subject to our weighting distribution. So we're going to compute the expectation of the quantile of our judgment function subject to the weighting distribution, and that's $333,333. Remember when we did order distributions, and we looked at what was the mean of the order distribution, 2 draws, pick the worst, and we got exactly the same number. Is that a coincidence? And it is not a coincidence, because this method of spectral measures can emulate any order distribution just by setting our weighting distribution to be a member of the beta distribution family. So let's remember a few facts about the beta distribution. The beta distribution has a distribution domain from 0 to 1. Remember, that's one of the things that we needed. And so long as the second parameter to the beta distribution is bigger than the first parameter, the beta distribution, so long as the first parameter is 1 and the second parameter is bigger than the first parameter, then it's going to be a monotonically decreasing, or at least non-increasing PDF. Okay? So we could just take an example of this. Here's the PDF of the beta distribution, first parameter 1, second parameter 3. We compute its monotonicity, and you can see that it's going downhill. And in fact, we could compute the expectation of the quantile function of J, our judgment distribution, with respect to this beta distribution, and it's $250,000. And by the way, let's just look at the PDF of the beta distribution of 1, 2. And you'll see it's 2 times 1 minus x. Let's look at the PDF of the triangular distribution. 0, 1, peak at 0 of x. And you'll see they're the same thing. That is, the triangular, this particular member of the triangular distribution firm happens to have the same PDF as a particular beta distribution. And in fact, you can kind of think of this triangular distribution as being a special case of the beta distribution. Okay? So, and indeed, with a little bit of algebra, we can come up with a general formula. That is, we can say, find me the values of A and B such that the expected quantile is equal to, this was that formula for the order distribution that we showed earlier. Let's go up and see if we can find that formula. Here we go. This is the mean of where you have D draws and you want the ith worst. That's the valuation created by the order distribution. And let's see if we can emulate an order distribution using this more general approach called spectral measures. And indeed, chunk, there we go. Here's our formula. It's a little bit hard to follow, but supposing, for example, that we want, let's actually put some examples in here. Let's do this, and let's find out what values of A and B we need in order for this to work out. So we will let I go to 37th. We want the 37th worst from 62 draws. And let's see if we can get this to work. All right. And so it's going to tell us that so long as A is 37B divided by 26, this will work. So, I guess what I'm trying to explain is that one virtue of spectral measures is that it can emulate order distributions. But unlike order distributions, we can do more. So supposing, for example, I believe that the proper weighting is a truncated gamma distribution. Here's a picture of a truncated gamma distribution. And you can see it's only slightly downward sloping. This would correspond to not a lot of risk aversion. These outcomes are not weighted that much less. These good outcomes are not weighted that much less than these bad outcomes. And so now we can use this approach of the expected quantile to actually compute how much our lawsuit is worth. And that's the exact value, and it's printed out an interim value along the way through my use of the echo function there. Okay, so we could do this with far more than J, At some points, you may need to move in your programming from expectation to a function called nexpectation, which uses a little different measures when you can't come up with an exact formula. But really, the principle is the same. What we're trying to do is to calculate the expectation of the quantile function of the judgment distribution subject to a non-increasing weighting distribution over the intervals 0 to 1. Okay. Obviously, there's a lot more to it than what I've presented. So you might be concerned about when you're going to get paid. Money today tends to be worth more than getting money a few years from now. There are obviously settlement, litigation costs that need to be taken into account. There are strategic considerations. You don't make your best offer first usually. There may be contingency fees so that the client doesn't get the entirety of the judgment. All of this is great, and you can add many layers of complexity to the valuation of lawsuits. But what I wanted to show here is how our understanding of statistics can inform fairly simple yet powerful models of valuation of lawsuits. There is also, you should know, an appendix in this notebook which starts to think about, well, how do you actually get a utility function? How do you get a quantile weighting function? And how do you get a judgment distribution? I think those are best read and not covered in the video, and so I will leave them to you. Thanks.